So this problem tells us that we have 2-point charges, one of 10 nanocoulombs and another of negative 10 nanocoulombs, and that they're separated by 15 millimeters of distance. And in order to calculate the force between these 2-point charges, the amount of force that this point charge exerts on this point charge and this point charge exerts on this point charge, we're going to use Coulomb's law. So let's start by gathering all the information that we have. So we know that our first charge has a charge of positive 10 nanocoulombs. Our second charge has a charge of negative 10 nanocoulombs. The distance between them, r, is 15 millimeters. So I can already tell right from the start that I'm going to have to do some conversions. So I have 10 nano, milli, and so these are going to need to be converted into coulombs and meters because our constant, epsilon naught, which is, in this case, we're going to use the permittivity of free space, even though the problem tells us that this is being done in air, because the permittivity of free space and the permittivity of air are basically the same. Okay? So let's write out our Coulomb's law equation. So I know force is equal to 1 over 4 pi epsilon naught times the product of our two charges, Q1, Q2, over the distance between them squared. Okay, so now all I have to do is plug in the numbers. 1 over 4 pi epsilon naught. Q1 is 10 times 10 to the minus 9 coulombs. Q2 is negative 10 times 10 to the minus 9 coulombs, divided by the distance between them squared, which is 1.5 times 10 to the minus 2 meters squared. So I'm in meters and coulombs, so I know that I've done it correctly. I multiply and divide and finish the calculation, and I get 4.0 times 10 to the minus 3 newtons. So that means that this charge is feeling a attractive force for this charge of 4 times 10 to the minus 3 newtons, and this charge over here is feeling an attractive charge of the exact same amount from this charge over here. So every action, there's an equal and opposite reaction. That's shown here. This one exerts a force on this one of 4 times 10 to the minus 3 newtons. This one exerts a force on the other one of 4 times 10 to the minus 3 newtons. So let's try another problem using Coulomb's law. So in this problem, 2-point charges of magnitude plus 5 coulombs, or plus 5 microcoulombs, and plus 3 microcoulombs are separated by a distance of 1.5 meters in a liquid that has a permittivity of 2.3 times 10 to the minus 11 coulombs per Newton meter squared. So this one's different than the previous problem where we assumed that the permittivity was that of free space. Now we're assuming that it's a different liquid, or it's a liquid that has a permittivity listed here. So let's compile all our answers, or our information. So Q1 is going to be 5 microcoulombs. Our second charge is going to be positive 3 microcoulombs. Our distance between these guys is going to be 1.5 meters. So that won't need a conversion, but these microcoulombs will. And our epsilon, our permittivity value, is 2.3 times 10 to the minus 11 coulombs squared per Newton meter squared. Okay, so let's start by writing out our Coulomb's law. So force is equal to 1 over 4 pi epsilon. Notice I don't put a not here because we're not dealing with free space, we're dealing with a liquid. The product of our charges, Q1 and Q2, over our distance squared. So force is equal to 1 over 4 pi. I'm going to write my epsilon value in there, 2.3 times 10 to the minus 11. Our charges are positive 5 times 10 to the minus 6 coulombs. And so I converted from microcoulombs to coulombs there. And 3 times 10 to the minus 6 coulombs. So I converted that to coulombs also from microcoulombs. I divide by our distance squared. No conversion necessary because it's already in meters squared. I multiply it out, I divide, and I find that the force in between these two objects is 23 millinewtons. Okay, so notice that the value of this force is positive. So it's positive, right? And if it's positive, that means it's a repulsive force. Sorry, repulsive force. So that means that these two positive charges are pushing away from each other. In the previous problem, we had a negative value for force, or we should have, if I'd done it correctly. And you would have seen that since it's a negative value, these two forces want to pull toward each other. It's attractive if it's negative. Okay? So negative is attractive, positive is repulsive.